next section of physics for us, which is a very interesting and very important section of physics, which is called the Newton's laws of motion. So this is going to be the next chapter for us. Newton's laws of motion, or basically the study of forces, you can say in another sense. So I have sent you some theory notes related to this in a PDF also. You can start reading through that part also. So let us first of all list out the 3 laws of Newton, which I'm sure all of you are aware of. So the first one is the law of inertia, or it is the property of inertia. So as all of you know, it says that any body or particle possesses a property called inertia, whereby it tends to oppose any change in its state of either rest or uniform motion. Okay. So let us understand this this law, this principle of inertia, with some examples so that it makes it more clear. So for example, if we have a body which is at rest, so body is lying on a frictionless surface at rest. We have block at rest. Now we know that it will not move it will not move until and unless some external force acts on it. Okay. So that is the property of inertia, that it tends to, it doesn't matter whether it's a friction surface or it's a frictionless surface. At this stage, let's treat it as a smooth surface. So it is frictionless. But we know that it will not move until and unless there is. So this tendency for it to not move, that means it resists a change in its state of rest. And the more strongly it resists that change, the more inertia we'd say it has. So a body having more mass has more inertia compared to a body having less mass, because it will require a larger amount of force to make its state of rest change compared to the body of lighter mass. So that is why, so this type of inertia is called the inertia of rest. When a body is at rest, and the property whereby it opposes the change in its state of rest, that property is called the inertia of rest. Okay? And that property in general is called the inertia. Another example is inertia of motion. Now, for example, we have a situation like this, that the same block, but it's already set into motion. So we've already set it into motion. So let's say we have got a body of mass m, which is moving with the speed v along a frictionless horizontal surface. So it's a smooth surface. Now we know that this body will continue in its state of uniform motion. So in other words, its velocity will remain constant until and unless again some external force acts. Acts on it. So that again is your property of inertia. It has a tendency to continue in its state of uniform motion. It will continue in its state of, but in this case, it is its state of uniform motion. So, so this is again the property of inertia. It has a tendency to continue in its state of uniform motion. It opposes any change. So that is the property of inertia. So for example, to stop the body, so for example, to stop it, an external what we call force or impulse, we'll get into the definition of impulse very soon, is needed. Okay. And we'll say the more the inertia of the body, that is in this case in terms of momentum, the more the momentum of the body, which we can define by a vector called P over here, which is mass into velocity. Okay. So the more the momentum, the more the inertia, so more the impulse needed to stop it. So this is an example of inertia of motion. And inertia of motion can be measured by the linear momentum. So for example, two blocks having the same velocity, but one having greater mass than the other has more inertia. Even though the velocities are same for the two blocks, but the heavier one will have more inertia. Therefore, it will require larger amount of impulse to stop it. Okay. Or two blocks of same mass, but moving with different velocities. The one having the larger magnitude of velocity will have more inertia. So in order to stop it, we require a larger amount of impulse. Likhit, just to answer your question, this is the Blue House combined with the non-integrated batch. I have mentioned that in the beginning. Okay. And there's nothing not to understand in this beta. This is the first lecture we are having of Newton's laws of motion. And I'm just listing out the laws of motion, which you are aware of from class 9th, I think. Okay, so this is the first law which I'm listing out. Okay. So it is the law of inertia. Okay. That is, this is the statement of the law of inertia. So those who have just joined in, you can just go through this section once. Okay. But really, we haven't really started any of the applications yet. I'm just listing out things that you already know, which is the statement of the three laws. So you can just go through this once and understand this. Yeah, you can write this down. Yeah, like what is the confusion about? Please tell me. What is the question? The first of Newton's laws is called the law of inertia. So that says that any body possesses this property called inertia, whereby it tends to oppose any change in its state of rest or uniform motion. Okay. So now I'm explaining the inertia in two different situations. One is inertia of rest, which I'm explaining in the first example. So you have a block which is at rest on a frictionless surface. Now it will tend to have a continuation in its state of rest. And to change it from its state of rest to a change of motion, we'll have to apply some external force on it. So that kind of property of inertia is called the inertia of rest. So that is measured by just the mass of the body. A heavier body has more inertia compared to a lighter body. The same amount of force acting on two blocks, the lighter block will have a greater will have a lesser tendency to oppose the change in state. The heavier block will require or will show a larger tendency to change its state of rest compared to the lighter block. Why? Because its mass is more. So that property is called the property of inertia of rest. Okay. Whereas the second example I'm showing you is an example of inertia of motion. Now consider a block that is moving with some velocity on a smooth frictionless surface. Okay. Now you know that it possesses this property that unless we apply an external force to it, it will just continue to move with a constant amount of velocity. Or in laws of motion language, now we say it will continue to have a uniform momentum, that is mass into velocity, until and unless we apply some external force on it. So that until and unless term, that is what is the property of inertia. It resists the change in inertia until and, or in this case the change in momentum, until and unless an external force is acting. So that is the inertia of motion. And inertia of motion can be measured by the amount of momentum. So if you compare two blocks having different momenta, now to bring both of them to rest, for example, you have to apply some impulse, that is force multiplied by time. But which one will require larger impulse to bring it to rest? The one having more momentum. So even if they have same velocities, if one block is heavier than the other, then the heavier block will require more force to bring it to rest, more amount of impulse to bring it to rest. So we say it possesses more momentum, or in other words, its property of inertia is more compared to the property of inertia of the lighter block, which might be moving with the same velocity, but it has less momentum. So property of inertia here is measured by the property of linear momentum if it is already in motion. Okay. Or another example would be that suppose we have, okay, Samantha, I'll scroll up. Yeah, then they have the same momentum. That's always possible. For example, 2 into 5 kgs, and the other one must be 5 kgs into 2 kgs. So they'll have the same amount of inertia then. Or in those words, we will say that they have the same amount of momentum. Okay. So Aditya, to answer your question, the first block, 5 kgs into 10 meters per second, has 50 kilogram meter per second momentum. The second one has 1 into 100 or 100 kilogram meter per second. So the second one has more momentum. So it requires a larger amount of impulse to bring it to rest. Okay. So this is what we mean by the property of inertia related to the property of momentum in this case. Okay, so are both examples clear? Okay, good. Now, for example, you have something like this. Let's say, okay, Pratyush, just a second. Okay. Okay, done, Pratyush? Okay. Now, another example to understand this property of inertia would be something like this, that imagine again on the surface of a carom table, you have a carom coin which is moving with a velocity like this. So as it's moving like this, at some stage, it collides with something else, which applies this kind of a force on it. So it applies what we call an impulse. It is force into time. So that might now cause the body to change its direction. It was going like this and an impulse acted like this. So now its momentum became like this. Let's say it became like this. The velocity changed direction. Okay, so you can see that its initial momentum was in this sort of direction, mv naught. Its final momentum is now in this sort of direction. Yes, there's a lot of application of vectors in this. So you can see that its final momentum is supposed like this. So this is the final momentum. And this was the initial momentum. So to change the initial momentum into the final momentum, you need to apply an impulse like this. And that impulse F delta t would be equal to the change in momentum. Okay, so that would be equal to m into final velocity minus m into initial velocity. Let's say like this. So its direction would be something like this. Okay. So now see here what is happening. Not only the velocity of the object's magnitude is changing, but the direction is also changing. So we can observe how impulse momentum or the concept of inertia acts over here like this. Okay, so this was going in a state of uniform motion like this. It was going like this in uniform motion. Okay. And now, if I want to change that uniform motion in direction, it has to turn like this or something like this or turn like this. We have to apply some external impulse. So again, we can see that to change the uniform motion in direction or magnitude or both. We might be changing both the magnitude and the direction. Okay, what is needed? External force is needed. External force or impulse, that is force acting over a period of time, is needed. Unless there is an external force or impulse, there is not going to be the change in uniform motion. So that property of the body is again inertia. That property of the body is inertia. The property by which it will tend to resist any change in its uniform motion. It will tend to go in the same direction at the same magnitude of velocity. It will neither tend to change its direction nor change the magnitude of its velocity until and unless there is an external force or impulse. Okay? Yeah, I will define impulse in detail. Right now you can think this impulse is, very simply, impulse is force multiplied by time. But the actual definition is a little bit more complicated. So when force acts over a certain amount of time, the force multiplied by time is what we call impulse. So inertia is a property. So Piyush, to answer your question, inertia is a property that any body possesses, whether it is in a state of rest or in a state of uniform motion. Okay, so that covers the first statement. Now let's come to Newton's second law. So the second law, as you know, is now giving you a more quantitative definition. The first law is just like a qualitative definition. Inertia नाम का कोई property होता है, but neither the first law gives you any formula for it nor any mathematical equation for it. Okay? So inertia is just a property we understand through all these examples, that whether the body is at rest and we want to bring it into motion, or it's already into motion but we want to slow it down or we want to stop it, or it's moving and we want to change its direction of motion, or we want to change its magnitude of velocity, or we want to change both the direction and magnitude. Whatever happens, we want to bring any change in its state of uniform motion, we have to apply some external force on it. On its own, the body will not change because it has the property of inertia. That property of inertia dictates the body क्या चाहता है, it wants to continue to maintain its state, which is either of rest or of uniform motion. So that property is called inertia, and that is nothing but the first law. The first law just defines that property as inertia. Okay, is the point clear to all of you? Yeah. Yes, it's okay. You can take down these points later also in detail. Right now, you can just make a brief note. So Newton's first law, you understood what it says, that it's the property of inertia. Okay. Now let us come to the Newton's second law, which is the quantitative law, which gives us the formula or the mathematical definition. So Newton's second law क्या बोलता है that the net external force acting on a body equals the rate of change of its inertia, sorry, of its momentum. Its rate of change of momentum. Okay. So mind you, the statement does not say net force is equal to mass into acceleration. Statement says, so what is the equation form of it? That the net force is equal to, now that you understand differentiation, it is instantaneous rate of change of linear momentum. So this is the proper mathematical definition of Newton's second. So this is where you want to pay maximum attention now, because actually the first law is contained within the second. So इसमें क्या हो रहा है? Let's understand each term. Left hand side, this is the net external force. So in other words, it is the vector sum of all forces acting on the body. So I'll come back to this statement. I'll give you time to write down it. But let's first understand this. So suppose this is a particle on which there are n number of forces acting. Okay. So there are forces F1, F2, some forces are pulling it, some forces are pushing it. Like this. So there are n number of forces acting on the body. So these are all forces acting externally. Some external agents are applying these forces. And like this, there are more forces. Let's say the last one, the nth. So suppose forces F1, F2, etc. up to some nth force act on a body. Okay. Then what we mean by the net external force acting on it is the vector sum of all these forces. So vector operation of addition of all these, or what in summation language we can write as F net is summation. This symbol is used for summation of F with the index I going from 1 to n. So this statement is just a mathematical way of writing this other statement. This symbol is called the summation symbol. And what we write below it is the lower index and this is the upper index. So when we expand this term, it basically means this, that the value of I is going from 1 to n. So it will be F1 plus F2 plus F3 up to n. So I is called the index. So now just take some time to write this down. We'll come to the right hand side of the equation also, rate of change of momentum. But first write down up to net force. What is the meaning of net force? So it is nothing but the vector sum of all the forces that are acting on the body. If there are 2 forces acting on the body, it is just F1 plus F2. If there are 5 forces, it will be F1 plus F2 plus F3 plus F4 plus F5. Like that, if there are 100 forces, it will be up to F100. So this is the statement of Newton's second law. You can write it down. And this is the Newton's second law in mathematical form. This is the mathematical form of Newton's. D कहाँ पे बेटा? कोई D नहीं. अच्छा, d by dt, that is rate of change. That is instantaneous rate of change. So I'll come to that side. Differentiation. You started differentiation, right? Yes, you write this down. Yeah. So वो differentiation है. It is differentiation of momentum with respect to time. Like you write dy by dx, na, rate of change of y with respect to x. Like that, it is rate of change of p vector with respect to time t. So I'll explain the right hand side. First, write down about net force, which is on the left hand side. Yes, mass isn't always constant. That's true. Okay, so next, how do we write the net force, which is on the left hand side? We can write it as the summation of all the forces. It is the net external force. So that means it is the vector sum. It is the vector sum of all the forces. Whatever number of forces. So ये जो vector sum लिखते हैं, इसको लिखने के दो तरीके होते हैं. Either we can write it as just addition of all the vectors, or we can write it in the summation method, which I have shown below. So just write this down first. So n forces acting on the body. That is what this diagram is showing. That there are a number of force vectors which are acting on that body. So next step, when we are doing this vector sum, another way of writing this is by the summation method, where the lower index shows the first term. So I equal to 1 means the first term will be I replaced with 1. And the upper index, capital N, shows the last term. So it will go from 1 to n. So if I replace capital N here with 50, that means there will be 50 terms over here. F1 plus F2 plus F3 up to 50. If I replace I with, for example, 5 and N with the lower index has 5 and the upper index has 10, then there are again only 5 terms because it is F5 plus F6 plus F7 plus F8 like that. 6 terms in fact, 6 to 10 including both. So upper index is the maximum value of capital N or of I, and lower index is the minimum value. So that means the index I is ranging between the lower limit, which is I equal to 1 in this case, to the upper limit, which is I equal to capital N. Okay, so that is about the net force. Okay, so don't worry, we'll be doing so many questions, you'll understand how to do this summation. Now the right hand side, on the other hand, and the right hand side, that thing, dp by dt, the technical term for this is instantaneous rate of change of momentum, that is the vector p, with respect to time, that is small. Okay. So as you know, instantaneous rate of change का मतलब क्या होता है? It is, as you must have studied in differentiation, it is the limit delta t tending to 0 of delta p by delta t. So instantaneous rate of change is nothing but rate of change in a very small interval. That is delta t tending to 0. So it is calculated by those differentiation methods which we have done. It is nothing but that. The same formula that you learned in differentiation, those will be applicable. So in differentiation, for example, you've learned that dy by dx is defined as the limit delta x tending to 0, delta y by delta x. For example, you know that if y is equal to x to the power some n, then dy by dx becomes n into x to the power n minus 1. So that kind of thing. For example, if momentum is equal to some constant into time cube, where alpha is a constant, then dp by dt will just become differentiation of alpha into p. So alpha will come outside into differentiation of p cube, so that it becomes p square. So it becomes 3 alpha p square. That is what was dp by dt. Is that same methods of differentiation that you learned in calculus. If alpha is a constant here, this is how this will be. So only notice that here I have written it as a scalar equation because I am assuming it's one dimensional. But in general, it is a vector equation. So it is the instantaneous rate of change of vector momentum with respect to time. That is the right answer. So my equation now becomes that net force equals to the rate of change of momentum. This is the statement of Newton's second. The next thing is इसमें momentum क्या होता है? Where P is nothing but mass into velocity. The quantity P is called the linear momentum. Okay, or in short, we just call it the momentum. The linear momentum of the body. So write this one down first, then I'll explain to you more terms. Okay, so statement of Newton's second law, I hope is clear to all of you that net external force equals to the rate of change of momentum. I think you shall explain here. Don't keep sending me the same message. I told you I'll explain more things as we go along. First, write down up to here. Have you understood what is rate of change of momentum? Have you understood instantaneous dp by dt? Okay, good. Now wait for the other things. Okay, so hope you understood. Yeah, what we've written on the right hand side is the basic formula of differentiation, which you know. Just to show you that this differentiation is the same thing that you are learning right now in calculus. That dy by dx, first of all, it is defined as the limit delta x tending to 0 of delta y by delta x. That is the definition of instantaneous rate of change or differentiation of y with respect to x. And the formula, the most basic formula that you know is the power rule. That if y is x to the power n, then dy by dx becomes this. So that is why, for example, differentiation of x square, you know, is how much? It is 2x. The differentiation of square root of x, for example, you know, is how much? It is 1 by 2 root x. Because this can be treated as x to the power half. So you use this formula where you put the value of n as half. So get this. Okay. So like that now, for example, suppose I said linear momentum depends on time like this. Suppose I had a situation where linear momentum varies with time t like this, where alpha is some constant. Then what would be rate of change of linear momentum? The rate of change of linear momentum would be differentiation of this term with respect to t. So because alpha is a constant, it will come outside into differentiation of this term t cube, that will become how much? N into t to the power n minus 1, so 3t square. So the differentiation of momentum with respect to time in this case will become like this. Okay. So this is just an example of how we can execute this equation if we know the linear momentum as a function of time. Now let's come to Newton's second law. Now we come to the very important aspect that suppose we are dealing in Newton's second law with a body or a particle. Okay. So in case the second law is being applied to a body, or typically what we call a rigid body. Rigid body means its shape and size is not changing, or a particle, such that the given body or particle is not changing in mass. That is, neither mass is being added to it nor its mass is disintegrating on the momentum. So that means when we talk about the linear momentum, P is equal to m into v. Here m is constant. But when we are dealing with this kind of situation, so then the rate of change of linear momentum will become differentiation of mass into velocity. Now, because mass is a constant, it will become mass into rate of change of velocity. Now, in calculus, you know that rate of change of velocity is nothing but instantaneous acceleration. So, rate of change of momentum will become nothing but constant mass into acceleration. Because acceleration is defined as instantaneous rate of change of velocity. This is the instantaneous acceleration. This is nothing but the instantaneous rate of change of velocity with respect to time. So that is the definition of acceleration. So therefore, we can say that the net external force, which is in general rate of change of linear momentum, becomes equal to mass into acceleration. But when mass m is constant. So the general equation is this one, but the specific equation becomes this. But this is now a conditional statement. This is a conditional statement, whereas this one is a general statement. This is conditional for mass being constant. So that is the difference between this form of Newton's second law, that F is equal to ma, and the proper statement of Newton's second law, that net force is equal to rate of change of momentum. So that rate of change of momentum, mass can be changed in various ways. Now, suppose we have a body which is disintegrating. Or take an example of a rocket system where the hot gases are constantly being ejected out because of combustion. So the total mass of the rocket is constantly decreasing. Or take the example of a conveyor belt. Mass is constantly being added to it. So you can see in these cases, the mass of the body you're talking about is not constant, it's variable. Take the case of a dumper truck which is moving, and as it is moving, some harvester is constantly adding grain onto the dumper truck. So the mass of that body you're considering, which is the truck, is constantly increasing. No, I just explained to you, it will not be constant. You can have a moving body, while it's moving, its mass is varying. And I've given you the actual examples of these. These are actual things which happen in the world around us. Consider a BMC tanker with water leaking out from the tap at the back. So as the tanker is moving, उसका mass घट रहा है ना बेटा. So even as it's in a state of motion, its mass is varying, either increasing or decreasing. So these are examples of what we call variable mass systems. So just make a note of this first, then I'll explain the variable mass system also. So finally, when we write Newton's second law as rate of change of momentum, it's a general statement. It's a general statement of Newton's second law. But when we write it equal to ma, F equal to ma, it's a conditional statement. It is only applicable to such bodies with a mass constant. Which also means that when the mass is not constant, we cannot say F is equal to ma. Then it becomes something else. Have you studied something called product law in differentiation? People, have you studied product law? Okay. So some of you might have, some of you might not have. Product law will not really become significant just now, but it's okay. So, in mind, if the mass of a body is not constant, or it is variable, then the net force that we write as the rate of change of momentum will not be equal to, it is not equal to m. So this is something to keep important to keep in mind, that we can't use the equation F is equal to ma in the case of variable masses. So for variable mass systems, that is, mass is variable, the rate of change of momentum, which is rate of change of mass into velocity, it actually becomes rate of change of mass into velocity plus instantaneous mass into rate of change of velocity. This whole term actually becomes like this. Okay, so we will come to variable mass system in a different chapter, but just as a fact of general knowledge, you should know that whenever we are dealing with a body, mass is not constant but is variable, then we cannot use this equation that F is equal to ma. Instead, we make use of this equation. We will study this in a later chapter. So this will be studied, will be seen in the chapter system of particles later. In this chapter, we will only be dealing with systems which have constant mass. That is, system where we can say net force is equal to mass into action. So you need not worry about that second equation just now, but you will see that the justification comes from calculus. Those of you who have studied the product, differentiation of product of two functions, you can see that's what we are applying over here. Mass is varying with time and V is also varying with time. So we are applying the product rule. Rate of change of M into V is rate of change of the first thing multiplied by the second plus the first thing multiplied by the rate of change of the second. Yes, the UV rule of multiplication. Okay. So example of variable mass system is a rocket system. It ejects mass in the form of burning fuel. Form of burning fuel, or a conveyor belt. Mass is constantly adding. We're continuously adding mass in that case. Okay, I'll scroll up. Okay. Yeah, the acceleration is not constant. That means the net force is not constant. That's why we call it instantaneous acceleration. It could be varying with time also. Okay, so now let us understand a couple of examples of the application of this equation. For a body of fixed mass m, the net external force becomes mass into instantaneous axis. So let's understand this with a couple of examples. Suppose we have again that situation that we have a frictionless surface on which we have a block like this, let's say. Now this is a block which is of mass, let's say 50 kilograms, lying on a smooth surface. Gravity causes instantaneous acceleration. That's why when a body is in free fall, then the acceleration of the body is equal to acceleration due to gravity, which is small g, which is 9.8 meters per second. So this is a smooth surface. There's no friction on it. Now what is happening is there are, let's say, two people who are influencing the body. So one is, let's say, person E, who is pushing it. So person A is pushing, and on the other side, we have a person B who is pulling it, like this. And as a result of all this, what we are observing is that the body is moving with a horizontal acceleration of P. So now suppose what is given to us is that the person E is pushing the block along the positive x-axis with a force of magnitude, let us say 25 newtons. The person B is pulling the block also along positive x-axis with FP, which I don't know, such that the block is observed to have a uniform acceleration so 1.25 meters per second square along positive x-axis. So first of all, write Newton's second law equation in proper vector form. For the block, and secondly, determine F2, how much that is. It's a very simple question. Just try this out. Mind you that when we write this equation, net force is equal to mass into acceleration. F as a SI unit of newtons, mass as an SI unit of kilograms, and acceleration as an SI unit of meters per second. So the definition of 1 Newton is that it is 1 kilogram meter per second square. So make use of that definition. Yes, that's correct, Aditya. Correct, Sarvesh. Okay, correct. Piyush, that's correct. So when we write the equation in proper vector form, so what we'll see is ये जो ब्लॉक सरफेस पे लाई कर रहा है, now on this block what is happening is E is applying a force along the positive x direction. So you can represent the force that E is applying with a vector arrow like this. This is the force that E was applying. So we can write that as Ft. And B was pulling it also along the positive x direction. So we can also represent that by another arrow. But that's also along the positive x direction. And that combination is giving the body an acceleration along the positive x direction, which we had written as E. When we write Newton's second law, that net force is equal to rate of change of momentum. So यहाँ पे वो क्या हो जाएगा, mass into acceleration हो जाएगा, because mass is constant for the body. So that net force will be replaced with what? Vector sum of Fa plus Fb is equal to mass into acceleration. Now in this we can see that Fa was given to us as 25 newtons and it's along the x-axis. So that's the value. Fb is an unknown magnitude, but it's along the positive x-axis. So Fb is unknown. And acceleration was 1.25, but along the x-axis in meters per second square. And the mass was a scalar of 50 kg. So in terms of vector operation, you can see what we're doing is on the left-hand side of the equation, we are adding two parallel vectors. So they will just become the sum of the magnitudes along the same axis. And on the right hand side, we are doing a multiplication of a vector with a scalar, 50 kg into 1.25 meters per second squared along alpha. So this is the statement of Newton's first law. So properly substituted, it is this. And therefore, you can see that 25 plus Fp is equal to 25 into, we can write this as 2.5 or so 62.5 Newton per meter. So we can see that the magnitude of this force is nothing but 62.5 minus 25 or 37.5 meters. So this becomes the other answer. So this is the proper, you can say technical sort of way of applying Newton's second law, right from the equation that net force is equal to rate of change of momentum. जिसको कि मैं यहाँ पे क्या लिखूँगा, mass into acceleration, because I know the mass is constant. Then I go back to the diagram and I can see vertical forces are cancelling. I'll come back to that later. So the forces which are causing the change in momentum are nothing but the two horizontal forces that A and B were applying. And both of them were given to me in the problem to be along the positive x-axis. So I have shown the arrows like this because my x-axis is this direction and my y-axis is this direction. Okay, acceleration was given to us in the problem as 1.25 meters per second square, and the mass was given to us in the problem as 50 kg. So we just substitute the values along with the magnitude of A's force that was given. So the only unknown in the equation was the magnitude of B's force, and that we have found out. Understood now? So it's just a simple case of making a vector equation that the sum of two vectors on one side is equal to mass into another vector acceleration on the other side. So right hand side में हम क्या कर रहे हैं, as an operation we are multiplying mass with acceleration. So it's a multiplication of a scalar quantity with a vector, which you know how to do earlier. And left hand side में क्या करते हैं, we are adding up forces. So in this case it's a very simple addition. It's the addition of two parallel forces. And they are acting in the same direction. So in terms of vectors, we say they are parallel vectors. Okay, so hope this is clear, people. Displacement की बात हम बाद में करेंगे. In Newton's laws, right now we are not talking about displacement. That is now down to kinematics. No? We can see that if this body was at rest initially and its acceleration is along the positive x direction, so kinematics will tell you that its displacement will have to be along the x-axis. No? Its displacement cannot be in some other direction. You're understanding? The body was at rest initially and we started applying these two forces continuously. So इसका acceleration का जो भी direction है, displacement will have to be in that direction. It cannot be in some other direction. Understood, na, Sarvesh? Okay, now let's see a slightly more interesting example. No, so see, if a body is starting from rest, kinematics will tell you that displacement has to be in the direction of acceleration. It cannot be in some other direction. It's starting from rest, so acceleration का जो भी direction है, velocity will have to be along that direction. So obviously displacement will have to be along the same direction. Okay, now let's come to another example. Nee, Samad, that would be the case if they were acting in opposite directions. If FA and FB were equal in magnitude but in opposite directions, then they would cancel each other. The vector sum would be 0. But यहाँ पे तो parallel direction में. Okay, now let's move on to this next example, which is something like this now. Now this is a more interesting example. Okay, so let's say this is a sort of three-dimensional sort of diagram of a body lying on a plane surface, on a horizontal plane surface. Try and get this right. Somewhat right. Okay. So now let's say this is some kind of a body which is lying on a two-dimensional plane. This is lying on a floor. this is a smooth flow, frictionless. So यहाँ पे this is your vertical axis. Your gravity is like this. Acceleration due to gravity is pointing like this. This is your vertical axis. So this is vertical. Now what is happening is this body of mass m equal to, let us say, 20 kilograms this time, is now being pulled by two forces which are both horizontal, but they are along different directions in the horizontal plane. So one force is like this, and another force is like this. So F1 and F2. So F1 and F2 are horizontal forces such that they are at 60 degrees with respect to each other, and their magnitudes are equal to 10 newtons each. So the better way to understand the geometry of these forces is that, now imagine you are seeing the top view of this. So this is the block seen from top. From above. So here gravity is into the plane. In this diagram, gravity is into the plane of this. So this diagram में मुझे forces कैसे दिखेंगे? My forces will look like this. One of the forces is acting at this corner, and the other force is acting at this corner. Such that, see that that 30 degrees to this. Understood? Both the forces are horizontal, but they are not along the same axis. In the horizontal plane, they are along different axes. ऐसे add. This is F1. This is F2. So we have to find the acceleration of the ball. We block the acceleration. Just try this out now. So acceleration is how much? Remember, the mass is in kgs, beta, and the force is in newtons. So it won't be that large. Parth, Dhruv, and Aditya. Aditya, you got the correct answer. Viraj, correct. Dhruv and Parth, just check your how you're using the units little carefully. Prachi, check your calculation once more. So basically, this is nothing but vector summation. अपने को क्या करना है इसमें? We have to just do the vector summation correctly. So what we have to do here is, you can use component algebra or you can just use simple geometry. You can understand that in the horizontal plane, yes, that's correct. Atharv correct. Ranak correct. Okay. So in the this thing only, horizontal plane, we can just add two forces. So like this, F1 and F2. The angle between them is 60 degrees and their magnitude is 10 newtons each. So is that rhombus thing? No? You can see that the resultant will become this diagonal of the rhombus. You see that the net force, which is the sum of these two, will become this. This will be F1 plus F2. So the left hand side of Newton's second law, net force, is F1 plus F2. So it will be such that its magnitude becomes root of 10 square plus 10 square plus 2 into 10 square cos 60. So that is 10 root 3 newtons. Okay. And it will be along this bisector, you know. It will be along the bisector of F1 and F2. But in the horizontal plane, okay. So that is the net force. And net force is equal to mass into acceleration. So magnitude wise, we can say that net force is equal to mass into acceleration magnitude. So the acceleration will become 10 root 3 newtons divided by 20 kgs, or the acceleration will be root 3 by 2 meters per second square, or approximately 1.732 divided by 2. That is but this acceleration vector will be along which direction? Okay. Acceleration vector will be in the horizontal plane. Okay. Along the angular bisector of F1 and F2. So in that diagram that we drawn earlier, if the forces F1 and F2 were acting symmetrically with respect to these edges, they were acting like this. So because they were symmetrical, ये F1 ऐसा था, ये F2 ऐसा था, both of 10 newtons each, but both acting like this at 30 degrees to this, at 30 degrees to this. So we can see that the acceleration vector will be along this symmetry line. The acceleration vector will be along this line. Bisects the angle between the two forces. You take this as your x-axis. That also you can find by triangle law, or you know the rhombus property. Rhombus का property क्या होता है, that the diagonal bisects the angle. You can see that the vector parallelogram is a rhombus. Okay, so this is a very useful trick actually. The diagonals are angular bisectors. Okay. That's why it always bisects. Okay. So in this diagram, in this three-dimensional diagram, the acceleration vector will be somewhere like this. इसमें क्या होगा, acceleration vector ऐसा कुछ होगा. It's along the horizontal, but along this. In the diagram that I have shown below, in this one you can see that xy is the horizontal plane. The z-axis is the vertical plane. This is the view we are taking from above. This is the top view. The z-axis, which is coming out of the plane, that is the vertical axis. Okay. XY plane is the horizontal plane. Okay, now understood this? So these are examples. And different types of situations we need to understand. So it becomes whole chapter in itself. In terms of mathematics wise, मैं क्या solve करने की कोशिश कर रहा हूँ chapter में. It is as simple as this. और कुछ नहीं करना है. We have to always solve this equation where left hand side is the vector sum of all the forces and right hand side is nothing but mass into x. So we are solving this equation. F net is equal to F1 plus F2. So that we are trying to do. So that is equal to mass into x. Then the acceleration rate. Okay, so that's all. Right, so done, then it's good. Now we'll quickly review the other law and then come back to more examples of solving these kind of situations. So the third and final of the Newton's laws is, as you know, the action-reaction principle. It's very simple. Simply says that if a body, let's say E, applies a force, which we call the action, on another body B. Yes, every action has an equal and opposite reaction. Then B will apply an equal and opposite reaction force on P without fail. Okay. So in other words, for example, when the striker in your carom game is coming and colliding with one of the coins, so let's say it's colliding with the queen. So at that point of time, while they are in contact, while these two bodies are in contact, so let's say this is our body B and this is our body E. So while they are touching each other in contact, E will be applying a force on B, which will be, let's say, along this sort of direction. So this, we'll use that form of subscripts. This is the force on B applied by E. So this is the force on the body B. So that's why I written B first, applied by the body E. So that's why I written E after the comma. So let's say this is the action. So B will apply an equal and opposite reaction on it, which will be a vector which will be exactly opposite in that, but equal in magnitude. So the two vector arrows should be anti-parallel, so exactly at 180 degrees, but of equal length, because they represent, so this is, so they represent equal magnitudes. The force on the body E, okay, applied by the body B, which will now call the reaction in this case. If one of them is called the action, the other one becomes the reaction. So the statement of Newton's third law here will now become that the action is equal and opposite to the reaction. So this whole statement can be written in one simple mathematical equation, that the force on E because of B is minus of the force on B because of B. This minus sign in between the two just shows you that the magnitudes are same, but directions are opposite. Same magnitude, but opposite direction. So I'm sure all of you have felt the full consequences of this law. Okay. When you try to hit somebody, punch somebody, slap somebody, whatever hand or palm or whatever you use to do the punching or the hitting or the slapping, it experiences an equal and opposite amount of pain, okay, or an equal and opposite reaction force. So this is a common occurrence that we have experienced from childhood and felt the consequences of it also. It's one of the easiest of the three principles to understand. Okay, that every action has an equal and opposite reaction. At the same time, I'll tell you something interesting. It's one of the most misunderstood principles in Newton's laws. People very easily make a mistake in the application of this. And I'm going to discuss some examples and you'll see how that happens. Yes, all those angles and all you can easily find by vector principles. That's not a problem. Learned enough of vectors to calculate all of this. So now let me ask you a simple question and consider this carefully and tell me. So you have that very normal situation of the block lying on a smooth horizontal surface. At rest. This is a smooth horizontal surface. So if the mass of the block is 5 kilograms and the acceleration due to gravity is 10 meters per second square, then first of all, calculate all forces acting on the body of the block in magnitude and direction. Then secondly, for each of these forces, explain the reaction force by Newton's third law. So first of all, tell me how many forces are acting on the body. Tell me how many forces are acting. Yes, very good. And what are they? Yes, very good. There is gravitational force and there is a type of force which we call the normal reaction, right, which the floor is applying on the body. And they are each equal to how much? 50 newtons. Correct. Very good. Now you have to explain to me what is the reaction to this. Friction to यहाँ पे नहीं act कर रहा बेटा, because it's on a horizontal smooth surface, but we are not applying any external force horizontally. So there is no friction acting. Okay, so we are not applying this anything horizontally, no? So there's no friction to act. You're understanding the point? Okay, normal reaction opposes. Okay, so we have all established the answer to the first part. Okay, you've all got this correct, no problem. Okay, so the answer to the first part I'm just listing out. That there are two forces acting on the body. One is the gravitational force, which I'll write as mg, and the other is the normal reaction, and this is a type of force which is called contact force, because it's acting because of the contact between two surfaces. So that I'll write with a simple n. So further, if I want to explain this in the diagram, so on the body, there are two force vectors which are acting. One is the gravitational pull of the earth, pulling it down with mg, and the other is the normal reaction that the floor is applying on it upwards. You should be able to show this as exactly equal and opposite. So this is the normal reaction, and since the acceleration of the body is zero, it is at rest. So net force should be zero. So therefore, normal reaction should balance mg. So normal reaction magnitude is equal to mg, equal to, what is it now, 15 newtons. Okay. So this normal reaction is, you can say 50 j cap in newtons, and this gravitational force, you can say, is minus 50 j cap in newtons. If I take this to be my y-axis, this will be my x-axis. But vector notation is not required here because it's very simple direction. So you can see that. Okay. So that's the first part. That's done. Now my question is that what is the reaction force for the gravitational force, okay, and for the contact force? इन दोनों की रिएक्शन फोर्सेस क्या है? So what is the answer for A part? No, they are not action reaction of each other. Okay, so if you are saying that, so this is what I was saying, that many people make a mistake in the application of action reaction. If you say that for the A part, if gravitational force mg is the action, then the reaction to that, if you say that normal reaction is the reaction to that, that is wrong. Okay, the contact force is not the reaction for that. I'll explain to you why. Because see, it is not correct. Okay. Not correct. So let's see why it is not correct. So now let's talk about the gravitational force mg. ये जो force mg देखा है मैंने, this one. Who is applying the force? Who's applying this force? And who is experiencing this force? Who's experiencing the force? Yes, very good. Aditya Vikram Singh, your answer is correct. The block pulls the earth towards itself. Very good. Very good. That's the correct answer. So who's applying this force? Earth. And who's experiencing this force? The block. So this force that I've written, ये mg वाला जो force है, this is the force on the block because of the earth. You understand? This is my action. Now, if you talk about normal reaction, I'll show you why that normal reaction cannot be the reaction to this. You'll understand in just a moment now. So this normal reaction, who is applying it? And who is experiencing it? Who is experiencing it? So the table surface is applying it. The table surface or floor or whatever, the surface is applying it. So let's just say the surface is applying it. And who's experiencing it? The block. Okay. So the normal reaction force that I've shown over there, that is the force on the block applied by the surface. Okay. So how can this and this be action reaction? Remember, action reaction का concept क्या था? Force applied by A on B is equal and opposite to the force applied on B by B. This was the action reaction principle. So you can see that, therefore, for the gravitational force, that is the force on the block applied by the earth, this was minus mg j cap. If this is an action, the reaction to this will be the force that the block applies on the earth. And that will be interestingly plus mg. This will be the reaction. The thing is, we don't think about this force because the earth has infinite mass. compared to the block. So this is an action reaction point. Okay, so it's like this, that if this is the earth, your tiny little block is sitting over here. तो क्या हो रहा है, पूरा अर्थ का मास मिलके जोर लगा के ब्लॉक पे is applying a downward force like this. This is the force on the block applied by the earth. And the tiny mass of the block actually also applies a force on the earth, which is equal and opposite, which is like this. It is acting upward on the earth. This is the force on the earth. Okay. So the block applies an equal and opposite. Okay, therefore, upward force on the Earth's mass. But the thing is that force is negligible compared to the mass of the Earth. So now keep in mind that that force will have a magnitude of how much? Magnitude 50 newtons. But Earth's mass is how much? Earth's mass is huge. It's incomparable. So there is no effect. There is no effect of that. So that's why if you drop an object from above the Earth's surface, the object comes down with g, but you don't see the Earth going up with acceleration. You don't see the Earth going up. That acceleration is zero because the mass of the Earth is tending to infinity. Okay. But you take something sizable, like you take the gravitational pull of the moon, and you understand that yes, it does happen. There is tidal waves on the Earth. There's an effect of that. In fact, the moon's gravitation does create small perturbations in the Earth's own orbit around the sun. You would have heard about this. Okay. So if we take a comparable kind of mass, I mean, obviously the mass of the moon is a lot less than the mass of the Earth. Okay. The amount of force is same. इतना force Earth लगा रहा है body पे 50 Newton, body भी उतना ही force लगा रहा है. But the difference is body का mass कितना है 5 kg. Okay. So if the body was under free fall because of that, it would create an acceleration of g. But would it create any acceleration for the Earth? No, because the Earth's mass is infinite. It's of the order of 10 raised to 5. Okay. So the whole point of action-reaction principle over here is that every action has an equal and opposite reaction. So what that means is that if the Earth pulls the body with an action, which is the gravitational pull of 50 newtons, the reaction to that is the body pulls the Earth towards itself with equal and opposite reaction. Of 50 newtons. And that is an action reaction pair. You understood? So this pair of vectors over here, that is the action reaction pair. Hope this point is clear to all of you people. Oh. Now next thing you'll see is for the second part. There's a normal reaction force that is acting upwards on the body. So if I just concentrate on that force for the moment. So this block पे ये force लग रहा है vertically upward. So this force is basically what? It is the force applied on the block by the surface. This is your normal reaction. So this is the contact force applied by the surface on the block. So what is the reaction to this? So the reaction to this is that the surface on which the body is lying, this surface, on this surface the body is also applying a downward force like this. That point on the floor is experiencing a force which is on the surface because of the block. So this will be 50 newtons downwards, and this is 50 newtons upwards. So this and this are in action here. So the force applied by the surface on the block and the force applied on the block by the surface. This is an action reaction. So this is the upward force of 50 newtons applied by the surface on the block. And that is equal and opposite to the downward force, the vertically downward pressing force of 50 newtons applied by the block on the surface. The block is pressing the surface downwards, so the surface is reacting by applying a normal reaction upwards. So this is your second part's action reaction. So like that, any force that you see in acting on a body, it will always have a paired up force, which is the reaction. But that paired up reaction force will not act on the same body. It will act on the recipient. Agent and recipient get interchanged. If A is applying the action on B, then B will apply the reaction on it. Both action and reaction cannot act on the same body A. Okay, people, so hope this point is clear over here. The concept of action-reaction pair. There's a mistake that 90% people make initially, that in this type of example, they'll say the normal reaction is the reaction force for the gravitational force, but that is wrong. Not in context of Newton's third law. Action-reaction pair has to act in this manner, which I showed you. Okay. So let us do a very simple, basic type of problem now based on this. Learning agenda and all is fine, but it's explained in your we'll be going by the same order as the module theory notes which I've shown, or that's the same order in which any of the reference books is presenting the chapter, which is H.C. Verma or René Galilei, or I've listed out the reference books for you. We'll be going in the same order of topics and all that. For example, we have a smooth inclined plane. Which is at an inclination of 37 degrees to the horizontal. So this is a smooth, or what we call a frictionless surface. Now on this we have a block like this. So the moment we release the block, it starts sliding down the inclined plane with some acceleration. Yeah, that friction will be taken into account much later. In the first part of the chapter, we will only be considering smooth surface. So a block of mass, let's say 2 kilograms, is gently placed on the inclined surface and released. So take G as 10 meters per second square, as we will be doing in most questions, and find the acceleration E in meters per second square. And secondly, the normal reaction contact force between the block and the inclined surface. And this is in newtons. Just try this out. Yes, very good. Aditya, correct. Normal reaction, anybody got it? Aditya, take GS 10 only, no? Yes, Kevin, correct. Normal reaction, Kevin, you got the correct answer. Aditya, correct. Good. Yeah, Piyush, it is 16 newtons almost. I don't know why you're getting 15.97. But if you just use the value of cos theta and sin theta, the standard ones, 37 and sin 37, you will get it exactly that one. Okay, so let me explain what is happening here. So first of all, one of the very important points to understand here is that normal reaction contact force, it always acts perpendicular to the plane of contact between two surfaces. In fact, the term perpendicular in maths is also called normal. Normal means perpendicular. So for example, if you have like a round object against a plane surface like this is the plane of contact. It will always act, the normal reaction will always act perpendicular to this. It will always act like this. So it will act along a line which is perpendicular to this. Like this. Similarly, if you have, I'll come back to that problem number. You have a cylindrical object which is resting against one surface like this and another surface like this. Suppose I have some situation like this. It's resting against surface 1, let's say, and this one is surface 2. So यहाँ पे जो point of contact है, उस पे normal reaction कैसे act करेगा? It will always act perpendicular to the plane of contact. So it will act along this line. The normal reaction applied by this surface on this will act along this line which is perpendicular. Similarly, the normal reaction applied by the other surface, this one, at this point of contact, will act along this line, which is again perpendicular to this surface. It will act like this. So similarly, when we have, like in this case, we have this block on the inclined plane. The inclined plane will apply a normal reaction perpendicular to itself. So here, whatever this angle theta is, now इस block के surface पे contact plane कौन सा है? ये वाला. This is the plane of contact between the block and the inclined plane. So what is the direction in which the normal reaction will act? It will have to act along this perpendicular direction. It will have to act along this line. This is the line which is normal. This is normal or perpendicular to the plane of contact. I'm coming to acceleration around that. So the normal reaction will act along that line. It will act the vector. It will act along this. It will have to act along this direction. It will act along. This is the normal reaction force. Okay. अच्छा, उसके अलावा what is acting on this? There is gravity acting. And what is the direction in which gravity is acting? Gravity is acting vertically down. Relax. Gravity cannot adjust itself according to the surface environment. mg, the gravitational force, is always vertically downwards. It has nothing to do with surface or anything. Okay. And you can see there is no other force. So there are only two forces acting on this body. Okay. There is only mg and normal reaction. Okay. So only two forces, gravitational force and the normal reaction. Okay. And you can see that they are non-collinear, that is not along the same line. So that means net force cannot be zero, because two forces which are non-collinear cannot cancel each other. So that means acceleration has to be non-zero. So the acceleration has to be non-zero. Now let's logically think the acceleration किस direction में होगा. So the moment you think, okay, logically which direction should acceleration occur in, you realize कि acceleration का direction क्या होगा, along the inclined plane. There's no way the block can move perpendicular to the inclined plane, because gravity is pushing it against the inclined plane. So mg is pushing it like this against the inclined plane. But normal reaction is kind of absorbing part of that mg. It's acting like this. So now it is all a matter of vector algebra. So we can see that if we do the vector algebra properly, we'll be able to find the vector sum of these two forces, in which direction it should be. It should be in this direction. In this direction. So to find out the net force, which is basically the normal reaction and mg's vector sum, which will become mass into acceleration, what we do is we just calculate the sum of these two. Now logically the way to calculate the sum of these two is very simple. देखो क्या हो रहा है. This is the direction of the inclined plane, which is making an angle theta with the horizontal. Just hang on a second, guys. I'll just stop the whiteboard and just give me a minute. I'll restart it. Giving me a lot of errors. Oh. So coming back here, this is my inclined plane, okay, which is at an angle theta to the horizontal. That theta is 37. So we'll plug in the value later. Now, just for convenience, I will show the block as a tiny particle. It doesn't matter whether the size of the block is large or small. Okay. तो उसमें देखो क्या हो रहा है, नॉर्मल रिएक्शन का जो फोर्स है वो इसके परपेंडिकुलर वाले एक्सिस में एक्ट कर रहा है. सो इट्स एक्टिंग लाइक दिस. It's acting along this axis, which is perpendicular to the inclined plane. So that's your normal reaction. And mg का जो force है, that is acting in the vertically downward direction. But at the same time, one thing that I know is mg is acting in this vertically downward direction. But at the same time, one more thing that I know is that the acceleration of the body is along which axis? It's along the inclined plane. So the acceleration vector here is in which direction? It's along this direction, along the inclined plane. That I know logically. So since the acceleration is along the inclined plane, what we'll do is we will take our x-axis along the inclined plane or along the acceleration vector, and y-axis will become perpendicular to the acceleration. So what we'll do is we will take the direction of our acceleration vector as our x-axis. We'll take this direction as our x-axis, and we'll take the direction perpendicular to it, that is this one, will become our y-axis. And next what we'll do is we'll resolve the forces along x and y-axis. So normal reaction is already along the y-axis, but mg has got both an x component and a negative y component. So next step is very important. So once we do this, we select our axis like this. Now why we have taken x-axis like this and not horizontal is for convenience, because the acceleration is along the inclined plane. So this is the convenient thing to do. This is the convenient choice of axis. Okay. So now we can see in the above diagram that my acceleration vector is along the x-axis. Why it is convenient is because now you can see that along x-axis, what should happen? The net x component of force should become mass into acceleration, and along y-axis, the net force should be how much? It should be 0, because there is no acceleration along the y-axis. See, x and y मैं कैसे भी ले सकता हूँ ना, they just have to be mutually perpendicular. So I just decided that I've taken this direction as my x-axis and this direction as my y-axis. I just decided. You can take this as negative x also, it doesn't matter. So along the y-axis, there is no acceleration. Whereas along x-axis, there is acceleration e. They act in the same plane, बिल्कुल. Two vectors, unless collinear, will always define a plane. No? Any two non-collinear vectors define a plane. So that is the vertical plane over here. Okay. So next thing is resolve the forces. Resolve the forces according to the axis. So when I resolve the forces along the axis, it's very simple really. I've taken x-axis like this, y-axis like this. So normal reaction is already resolved. So I don't need to do anything else to normal reaction. So normal reaction जैसा है उसको वैसे ही रहने देंगे. But mg we'll have to resolve. We'll have to see that mg has components. Mg has an x component and a y component, which we'll now have to calculate. So that is where we need this angle. Now this angle we can see will be theta. Why will this angle be theta? Because very simple geometry. See this vertical direction and this horizontal direction earlier. Inclined plane का जो ये. This is theta. So this angle here is 90 minus theta. So this angle will become theta. No, not z-axis, बाबा. Z-axis तो perpendicular है. Z-axis तो ये diagram के perpendicular है. How is gravity acting along z-axis, Piyush? Gravity is acting vertically downwards. Na? It's in the xy plane only. Understood? Gravity is not acting along the z-axis. The z-axis is perpendicular to this plane. It's a horizontal one. So mg को हम resolve करेंगे. So mg का ये component कितना हो जाएगा? When we resolve mg now, this component of mg, it will become mg cos theta. So that is the component of mg along negative y-axis. And this component of mg will become mg sin theta. That is the component of mg along x-axis. This vector mg in between, now it's divided into two components, mg sin theta and mg cos theta. Whereas, so what we can see now, next thing we can see is that mg sin theta becomes the net force along the x-axis, whereas n is cancelled by mg cos theta, because n is along the positive y-axis and this is along the negative y-axis. Okay. And we had seen earlier that the net y force was 0, whereas the net x component of force was how much? Mass into acceleration. So further, this equation will show us that mg sin theta is the net force which is acting along the x-axis, so it's providing an acceleration here, whereas this equation is showing us that n is cancelled by mg cos theta. These two forces are balancing each other, so there is no acceleration along y-axis, whereas this equation is showing us that there is an acceleration of g sin theta, or 10 into sine 37, so that is 6 meters per second square along x-axis, that is down the inclined plane. So down the inclined plane, there's an acceleration of 6 meters per second square. And this is also telling me that the normal reaction will become 2 into 10 into cos 37. So that is 20 into 4 by 5. So we have 16 newtons. So that will be the normal reaction. And this will be the acceleration. Okay, so this is how we apply the Newton's laws concept of it. There are two forces acting on the body. One is acting like this, one is acting like this. But together they are creating an acceleration in this direction. So that's why we resolve. Yeah, we've resolved using geometry only, but we have not used anything else. We have used the geometrical thing only. Na? A component mg cos theta, वो component mg sin theta. Okay. So let's go over the steps again. So the first thing that we did is we decided our choice of axis. So how we decided that because the body is accelerating along the x-axis, since the acceleration is along the inclined plane, therefore we are taking our x-axis along the inclined plane and our y-axis perpendicular. The convenient choice of axis is the. So having done that, next thing we want to do is resolve the forces. It become like this, and the rest of it is vector algebra. Okay. So just make sure that you revise this last question when you are going through today's notes and understand the resolution of the vector forces and all that clearly in the last example. Okay. No, it will be 37 only. The angle is 37. Okay. Just go through the diagram again and you'll understand. I've taken theta as 37, so that's why the angle with the y-axis will be 37. Because there is a right angle triangle which you have to add. I'd show you clearly in that. anyway, we'll be doing a lot of problems based on inclined plane, so we'll get used to this. But make sure that you understand all the steps in this problem when you are revising carefully. Okay. And I will send you the notes and the recording as well as the homework. Okay. So that's it for today, people. Just do a revision of the class notes and the lecture, and I will send you some work also from the module, etc. Yeah, Piyush, to answer your question, I have already sent the module notes in PDF form on the groups. So just find it in a group.